Good morning, everyone. This is Dr. T Thupal, Professor, Electronics and Communication Engineering of G. Pullai College of Engineering and Technology, Kurnool. As we have been discussing about GATE subject, which is called electronic devices, and yesterday we have learned about the basic semiconductor physics and its current flows and the types of semiconductors, which are nothing but a single type semiconductors and uh, crystal, single crystal and multi crystal semiconductors. And also we have learned about why silicon is best used material. Now today's class we will go with the enhancement of the yesterday topic, which is called Fermi level. Right. Now let us see what is the Fermi level actually. As we have seen about the valence band and conduction band, and the difference between valence band and conduction band is the energy, forbidden energy gap, which is called as Eg. But here, as electron is jumping from valence band to conduction band, then there is a level in between conduction band and valence band where the energy state is filled with 50% of electrons. That energy state where the energy level is filled with 50% of electrons, that level is called as Fermi level. And that energy state which is filled with electrons can be found by using a probability distribution function, which is called as f of E. It is nothing but given by a Fermi Dirac, where a scientist, and it is been called as Fermi Dirac probability density function, which is given by f of E. F of E is equal to 1 by 1 plus e power E minus Ef divided by kT. E minus Ef divided by kT. So here let us check for three cases here. How does electron occupies the Fermi level or occupies any energy level which is present in between valence band and conduction band. So here we have three cases here. Case 1, for example, if E is equal to Ef, energy level is equal to Fermi energy level, E is equal to F, then what is the probability of occupying an electron in which energy level? So it is given by F of E is equal to 1 by 1 plus e power. If E is equal to F, then it is E minus E, which is becomes 0. So that is equal to 1 by 1 plus e power 0 is 1, that is equal to 1 by 2, that is equal to 0.5. That is equal to 50% of energy states are filled with electrons. So that means an electron is jumping from valence band to conduction band, then 50% of electrons are occupied by that level. That level is called as a Fermi level, which is nothing but this one, Ef, where you can see here the 0.5, 50% has been occupied with electrons, which is a probability distribution function. I am taking on x-axis, and the energy level in electron volts, it is taken on y-axis. So you get 0.5, which is nothing but here, right? Similarly, apply for case 2, which is E less than F. If E is less than F, that means the applied energy level is less than Fermi energy level. Then let us check where the electron is jumping from conduction band to valence band and in which state it is being occupied. So E is less than F. F of E is equal to 1 by 1 plus e power. If E is less than F, what happens is, here you get, if you assume E is infinity, then if it is less than Ef, then you get here minus infinity, e power minus infinity. That is equal to 1 by 1 plus e power minus infinity t is 0, that is equal to 1. So the occupied energy states are 1. So the probability of occupying the energy level is 1. So this is nothing but 1, where the occupying energy state is 1 here. That means if E is less than Ef, this comes into picture, and the occupied energy states are having 1. The probability of existing is 1. And case 3, if you observe case 3, which is E greater than Ef, then probability distribution function f of E is given by f of E is equal to 1 by 1 plus if E is greater than EF, assume that E is equal to infinity, therefore, then you get here e power infinity. If E is greater than EF, so infinity minus EF, therefore, you will get infinity, e power infinity, that is equal to 1 by 1 plus e power infinity is infinity, that is equal to 1 by infinity, 1 by infinity is 0. So, that means the probability of occupying an electron while it is jumping from valence band to conduction band, then it is having a probability of 0. So, that means if E is greater than EF, where it comes into picture, this level the probability of occupying is 0, because it has been already occupied in the energy state and it is present in the conduction band. So, therefore, you get here the probability is 0, the probability of occupying is 0. So, this is the main important concept what we have in Fermi-Dirac probability distribution function. As you see, you can see here, as even temperature rises, some electrons have energy above the Fermi level. So, if temperature rises, what happens is, then the graph where it is original one is like this, then the graph goes like this. So, the occupied energy states will be increased here. And if again temperature increases here as higher temperatures, then see the occupied energy states, it is still more than that of the previous case, more than that of the previous case. So, here in this Fermi level, let us have a brief concept here with regards to one problem here. We will go with one problem here. This is the problem which comes under competitive exams. The probability that an electron in a metal occupies the Fermi level at any temperature T is T greater than 0 degree Kelvin. T greater than 0 degree Kelvin. So, the probability that an electron in a metal occupies the Fermi level at any temperature T is. So, what is that an electron in a metal? In a metal, you can see here we have a level, and here we have another level band. So, what is this band? This band is called as a valency band. This band is called conduction band, where electrons will be jumping from here and occupying the holes present in conduction band here, in turn creates a current flow. Now, here this is the energy gap, where it is approximately equal to 6 electron volts for insulator, and it is approximately equal to 1 electron volt for a semiconductor, and it is approximately equal to 0 electron volts for a metal or a conductor. So, here the problem it's been asked as a metal. Metal is a good conductor of electricity, so it is called as a conductor. So, metal is a conductor, so therefore, conduction band, valence band will be occupied, will be both will be overlapped, and therefore, because electron is already present in the conduction band, if electron is already present in the conduction band, so what happens? So, the probability that an electron in a metal occupies the Fermi level at any temperature T is T greater than 0 degree Kelvin, it is approximately, the probability is already been occupied. You can observe here the probability of f of E here, this is energy level here. So, here we have conduction band, here we have valency band. So, therefore, this is EC, this is EV, this is 0, and this is a Fermi level EF. Here it has been occupied with 0.5, here it has been occupied with 1. So, always the electrons are been already filled. So, therefore, what is the probability means? The probability of occupying, because here it has been already filled. So, therefore, f of E is equal to 1 for any temperature T greater than 0 degree Kelvin, right. So, the answer here is B. The probability that an electron in a metal occupies the Fermi level at any temperature T is, so what is that probability means? That probability is nothing but 1, it's equal to 1. The next concept, consider two energy levels E1 above the Fermi level and E2 below the Fermi level. That means, where we have Fermi level, the Fermi level is here, and here we have conduction band energy level, here we have valency band energy level, right. So, this is conduction band, this is valency band. So, Fermi level is occupied at center point now. Consider two energy levels E1 above the Fermi level. So this is above the Fermi level, I can consider this one as E1, and E2 below the Fermi level, this is considered as E2 below the Fermi level. P1 and P2 are the probabilities of E1 and E2. This is probability of this one is P1, probability of this one is P2. Being occupied by the electron respectively, then the conditions are given. P1 is greater than P2, P1 is equal to P2, P1 less than P2, P1 and P2 depend on number of electrons. Let us check what is the answer for this one, right? As we have seen already, according to Fermi Dirac probability density function f of e, we have f of e is equal to 1 by 1 plus e power e minus ef divided by kt. E minus ef divided by kt. So here, for example, here e minus ef, f of e for first case, if you treat this one as e greater than ef, then just now we have learned about Fermi level, f of e is equal to 1 by 1 plus e power infinity 1 by 1 plus infinity, that is equal to 0. That means this is the probability of occupying P1 if E is greater than EF, which is nothing but E1 is greater than EF. If E1 is greater than EF, then you get a 0 as the probability, right? In the second case here, if you get another thing, energy level is less than EF, case 2, that means what happened, probability density function f of E is equal to 1 by 1 plus, you get here e power minus infinity 1 by 1 plus 0, that is equal to 1, which is nothing but probability P2. That means this is energy E2 which is less than EF, then you get a probability density function as 1, which is nothing but P2. So therefore, here what about the probability for E1? The probability is P1, and for E2 the probability is P2. So therefore what happens is P1 value is 0 and P2 value is 1. So therefore P1 is less than P2. So this is the correct answer. P1 is less than P2. So likewise, the questions are being asked regarding a Fermi level and Fermi Dirac probability density functions. Next, we'll go with another topic which is called types of semiconductors and their energy bands. Types of semiconductors. As you know, we have already learned about a semiconductor where its conductivity lies in between insulator and conductor, and therefore its energy gap is approximately equal to 1 electron volt. So let us have different types of semiconductors there. So we have two types of semiconductors which comes into existence. They are intrinsic semiconductor and extrinsic semiconductor. So intrinsic semiconductor, let us go deep into the subject of intrinsic and extrinsic. Extrinsic semiconductor. In intrinsic semiconductor, it is also called as purest form of semiconductor. Intrinsic semiconductor is also called purest form of semiconductor. Actually, there is no current flows in a purest form of semiconductor. For example, if you take a silicon crystal and another silicon crystal, if you form a bond here, actually silicon crystal is a tetravalent atom where 4 electrons are lying at outermost orbit. So here 1 electron, 1 electron, 1 electron, 1 electron. So if you consider here electron, electron and electron, another structure with the silicon material, it is forming a bond with the another electron. So therefore the covalent bond is formed. There is no charge carrier which is free in order to get a current flow in this device. So therefore a current flow, if it wants to flow in intrinsic semiconductor, it's very difficult to obtain, and it is a very minute current at very higher energy levels it has been obtained. So because there is no free electron or hole which is present in this intrinsic semiconductor, which is a purest form of semiconductor. As you see in this structure, which is a two-dimensional crystal lattice of a silicon. Even though if you take for a germanium also, it's a tetravalent atom. The same concept arises for germanium material also, right? But here what happens, see, let us see. The number of electrons occupied in intrinsic semiconductor N is given by N is equal to, where the effective mass of electrons Nc into e power minus of Ec minus Ef divided by kT. This is the formula which we get for the concentration of electrons present in n-type semiconductor. And here also the concentration of holes which are given by Np is equal to Nv, where Nv is called effective mass of holes. Nv is called effective mass of holes. Nc is called effective mass of electrons. And Nv is called effective mass of holes. So we have a formula Np is equal to P is equal to, which is a concentration of hole, Nv into e power minus of Ef minus Ev divided by kT. So it is the holes which are lying below this Fermi level, so that's why it is written as Ef minus Ev divided by kT. And electrons which are lying above this Fermi energy level, as they are jumping from valence band to conduction band, so it's written as Ec minus Ef divided by kT. So if it is intrinsic semiconductor, number of concentration of electrons is equal to number of holes. So therefore N is equal to P is equal to Ni, where it's called intrinsic concentration, and its units are concentrations per centimeter cube or concentrations per meter cube. Now if you apply here N is equal to P is equal to Ni, then we get here Nc into e power minus of Ec minus Ef divided by kT, that is equal to Nv into e power minus of Ef minus Ev divided by kT, and that is N is equal to P is equal to, that is equal to Ni. So therefore we are making equally the concentration of electrons and concentration of holes. So therefore, so what we get here, so let us see here, Nc divided by Nv is equal to e power minus of Ef minus Ev divided by kT. This e power goes to numerator, you get here e power Ec minus Ef divided by kT. So that is equal to Nc by Nv is equal to e power minus of Ef plus Ev plus Ec minus Ef divided by kT, that is equal to Ec minus Ef divided by kT minus of Ef minus Ev divided by kT. So you get here minus Ef, therefore Ec plus Ev, so you get here that is equal to e power minus of 2Ef plus Ev plus Ec divided by kT. Okay, so that is equal to, even for intrinsic semiconductor we have Nc is equal to Nv. So therefore both gets cancelled, you get 1 here. So therefore here you get here Ec Ef is equal to Ec plus Ev divided by 2. That means for intrinsic semiconductor, the Fermi level lies at in between valence band and conduction band at center point, that is Ec plus Ev divided by kT 2. So here this is the Fermi level where it is existing for intrinsic semiconductors, which is lying at a center point, because Nc is also equal to Nv, effective mass of electrons is equal to effective mass of holes, as effective mass of concentration of electrons is equal to concentration of holes. So therefore the Fermi level lies at a center point here in between conduction band and valence band, which is given by Ef is equal to Ec plus Ev by 2. Similarly, let us go with extrinsic semiconductors. Extrinsic semiconductor, which is the impure form of semiconductor, it is also called as impure form of semiconductor. Impure form of semiconductor. where for this we need to add some impurities to the intrinsic semiconductor, so that extrinsic semiconductor will be formed. So here intrinsic, I can say that intrinsic plus doping is equal to extrinsic semiconductor. Intrinsic plus doping is equal to extrinsic semiconductor. What for doping here? Doping actually, it's a adding of impurities to intrinsic semiconductor, so that to make sure current flows in the device. But here in intrinsic semiconductor, it's very difficult to make sure current flows in the device. But here, by adding some dopants to intrinsic semiconductor, then extrinsic semiconductor will be formed here. So what are those dopants? This dopants, the process of adding dopants to intrinsic semiconductor is nothing but doping. So what are those dopants? There are two types of dopants, where they are called as p-type dopants and n-type dopants. P-type dopants are also called as acceptors, N-type dopants are also called donors, and these are also called as trivalent impurities. These are also called trivalent impurities. These are also called pentavalent impurities. These are also called pentavalent impurities. These are also called third group elements. Third group elements. These are also called fifth group elements. Fifth group elements. So these are the various types of dopants. For example, what are p-type dopants or acceptors, trivalent impurities, or third group elements? They are given by boron, aluminum, gallium, indium. They are given by boron, aluminum, gallium, and indium. Boron, its atomic number is 5. Aluminum, boron, aluminum, its atomic number is 13. Gallium, its atomic number is 31. Indium, its atomic number is 49. Similarly, the fifth group elements come into existence here. They are called phosphorus, arsenic, antimony, and bismuth. These are called as fifth group elements, where phosphorus atomic number is 15, arsenic atomic number is 33, antimony atomic number is 51, bismuth atomic number is 83. So here, as if you add boron material or aluminum or gallium or indium to silicon material or germanium material, then the majority charge carriers will be holes there and minority carriers will be electrons. Whereas here in n-type semiconductor, the majority carriers will be electrons if you add it to germanium crystal or silicon crystal. That means here for phosphorus 15, arsenic 33, suppose if you add phosphorus to germanium material or arsenic material, then the outermost orbit electrons contains here 5 electrons. That's why it is called as pentavalent impurities. Here the outermost orbit electrons contains 3. So that's why it is called as trivalent impurities. Here majority charge carriers will be holes. Here my majority charge carriers will be here electrons. Right. Now let us take an example and let us see. See the structure here. I am taking a boron material for p-type impurities, where boron material, its atomic number is 5. Therefore 5 means the first orbit is contained by 2 electrons. As you know that the second orbit is contained by 3 electrons. So that's why it is called as a trivalent impurity, as outermost orbit contains only 3 electrons. Now if you combine this boron material with the germanium material or silicon material, then let us see what happens. Here the germanium material, which is a tetravalent impurity, where 4 electrons are lying at outermost orbit. So here you can observe here, this is germanium, 4 electrons, 1, 2, here also 3, and here 4. Likewise 1, 2, 3 and 4, and it is combined with the boron. Boron here, it's a trivalent, 1, 2, 3 electron and 1 is a hole. 1 is a hole. So likewise, see, this electron and this electron forms a bond. This electron forms a bond, covalent bond. This electron forms a bond, and these are forming a bond here. But whereas this is having a hole here and this is having an electron here. Now, previously in intrinsic semiconductor, it's not happened here. There is no hole and there is no electron there, because number of concentration of electrons is equal to holes. So there is no current flow over there. Now here, just if I give a light energy to this electron jumps and fill into this hole and creates a current flow. Current flow definitely. So, but how much is the energy that we need to give here? How much is the energy means the energy I can give it as a 0.01 electron volts, which is existing for germanium. If I give just a light energy 0.01 electron volts to this electron jumps and fill into this hole, in turn creates a current flow. So likewise, the current has been existing in extrinsic p-type semiconductors. And here you can see here the concentration of holes, where it's nothing but P. It's also called as acceptor concentration, Na, and here already we have got P is equal to Nv into e power minus of F minus EV divided by KT. Ef minus Ev divided by KT. So this acceptors or holes, it's also been called as acceptor concentration Na, and the effective mass of holes Nv e power minus of Ef minus Ev divided by KT. So now bring this one to this side, you get e power Ef minus Ev divided by KT, that is equal to Nv divided by Na. So Ef minus Ev is equal to KT, you get Ln natural logarithm Nv by Na. So Ef minus Ev is nothing but KT Ln Nv by Na, or you can write this one as Ef is equal to Ev plus KT Ln Nv divided by Na. That means something has been added to valency energy level. So here you can see here something has been added to valency energy level. What is that something? Means KT Ln Nv by Na. So then you get Fermi energy level, and this Fermi energy level is very nearer to valency band. You can see here this is the Fermi energy level, and this is called acceptor energy level Ea, where holes will be present here. So therefore holes are present and they are very nearer to valency band. So you can have this formula, Ef is equal to Ev plus KT Ln Nv by Na. So this is what the derivations and equations for the p-type semiconductor. Let us see for the n-type semiconductor, taking into consideration the fifth group elements. It may be phosphorus, arsenic, antimony or bismuth. So this is regarding n-type semiconductor, and I am taking a n-type material which is called as a arsenic material, whose atomic number is 33, and if you draw energy band structure for arsenic, then the outermost orbit contains 5 electrons, because it is a pentavalent impurity material. So 5 electrons will be there. You can see here this is an arsenic, 5 electrons, 1, 2, 3, 4, because arsenic atomic number is 33. And 33, first orbit, how many electrons? 2 electrons will be there. Second orbit, 8 electrons. Third orbit, 18 electrons. So the remaining electrons are 5. 18 plus 28, 28 plus 5, 33. So therefore outermost orbit contains 5 electrons. These 5 electrons are, if it contains for arsenic, then it's called as a pentavalent impurity. So therefore you can see here this is 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. Now I am mixing this one with the germanium crystal or silicon crystal. Then what happens is, see here germanium is a tetravalent impurity. Here 1 electron, 1 electron. This is forming a bond with the arsenic material. This is also forming a bond with arsenic. This is also forming a bond with the arsenic. This is also forming a bond with arsenic. But this is This is also forming a bond with arsenic. This is not forming a bond with any other material. So this is called as a free electron, which tends for flow of electricity. Now, if I apply light energy to this electron jumps from this place and enter into another atomic structure which is contained by hole, and this electron filled by with this hole, then in turn current is flown in the device. Current is flown in the device. So, but how much energy we need to apply for this one means for n-type semiconductors, we need to apply for germanium crystals, we need to apply 0.01 electron volts, and if it is for silicon crystal, we need to apply 0.05 electron volts. So, this is the minimum energy required to detach an electron which is present in its covalent bond, so that it will make sure a current flow in the device. This is for germanium crystals and this is for silicon crystals. So, if it is germanium here, you can apply for 0.01 electrons, but if you apply for silicon crystal here, then you can go for 0.05 electron volts, so that current is flown in the device. Current is flown in the device. So, as you see here, we have already known about what is this n concentration of electrons. N is equal to, we have a formula, n is equal to Nc, effective mass of electrons, into e power minus of Ec minus Ef divided by Kt. Ec minus Ef divided by Kt, where it represents the concentration of electrons present in the device. Now, even concentration of electrons is also called as donor concentration. I can write this one as N is equal to Nd because they are called as donors. Electrons present in p-type impurities are called as, n-type impurities are called donors. So, therefore, N is replaced by Nd, effective mass is Nc, e power minus of Ec minus Ef divided by Kt. Similarly, you can go with bring this one this side, e power, you will get Ec minus Ef divided by Kt is equal to Nc by Nd. So, therefore, as you see here, Ec minus Ef divided by Kt is equal to Ln Nc by Nd, that is equal to Ec minus Ef is equal to Kt Ln Nc by Nd, or you can have Fermi level Ef is equal to Ec minus Kt Ln Nc by Nd. So, Fermi level is given by the subtraction of some value with respect to conduction band energy level. So, therefore, Ec minus Kt Ln Nc by Nd. So, therefore, it is lying very nearer to conduction band. So, therefore, you can observe here as Fermi level moves towards the conduction band and donor concentration is also nearer to conduction band. So, this is called donor concentration Ed, where electrons will be filled here, and therefore, this electron jumps from this point to this one just by applying a very small potential, which is nothing but if it is germanium 0.01, if it is silicon 0.05 electron volts, and the Fermi level is exactly lying at below this point, which is nearer to this conduction band, and this structure is exactly opposite to p-type semiconductors. And this is the detailed description about n-type semiconductors, where we have with respect to structure and with respect to formulas and with respect to design considerations here. Now, let us see some problems regarding this n-type and p-type semiconductors, where we will see over here like this. For example, this is one of the gate question. How to answer this type of gate question? See, in an intrinsic semiconductor, the free electron concentration depends on. In an intrinsic semiconductor, the free electron concentration depends on. As given, it's given by A, B, C, D options: effective mass of electrons, effective mass of holes, temperature of semiconductor, width of forbidden energy band of semiconductor. Now, in an intrinsic semiconductor, the free electron concentration depends on. As already we have discussed that intrinsic semiconductor means it's a purest form of semiconductor, and there the concentration of electrons is equal to concentration of holes, that is equal to intrinsic concentration Ni. And this intrinsic concentration Ni is nothing but we can write this one as concentration per centimeter cube, or it can be written as concentration per meter cube, which is nothing but Ni. Now this Ni is also been written as with respect to a formula. Ni intrinsic concentration is Ni is equal to, we have intrinsic concentration Ni as A naught T cube e power minus of Ef minus Eg divided by Kt, or A naught T cube e power minus of Eg divided by Kt, where Eg is called energy gap and A naught is a constant, T is a temperature. So I can write definitely this one as Ni is directly proportional to temperature T. Ni is directly proportional to temperature T. Okay. Actually, this formula exists for Ni square. Ni square is equal to A naught T cube e power minus of Eg naught by Kt, and therefore Ni square is directly proportional to T, or Ni is directly proportional to T power 1 by 2. So therefore, and T cube 3 power 3 by 2, therefore I can directly say that Ni intrinsic concentration is directly proportional to temperature. So therefore, in an intrinsic semiconductor, the free electron concentration depends on temperature of semiconductor, As you see here, the solution Ni square is equal to A naught T cube e power minus Eg naught by Kt, and Ni square is directly proportional to T cube, or Ni is directly proportional to T. So the answer is temperature of semiconductor. Next one, a silicon sample is uniformly doped. A silicon sample is uniformly doped with 10 power 16 phosphorus atoms. 10 power 16 phosphorus atoms per centimeter cube, and it's also been doped with 2 into 10 power 16 boron atoms. Silicon is also been doped with 2 into 10 power 16 boron atoms per centimeter cube. So borons means it's as you know that these are p-type semiconductors. Phosphorus, it's an n-type semiconductor. So these are called as donors, and these are called as acceptors. These are donors and these are acceptors. These are electrons and these are holes. So now we are adding hole concentration 2 into 10 power 16 for silicon, and we are adding electron concentration 10 power 16 phosphorus atoms. So therefore, here 10 power 16 electrons will recombine with the holes in boron atoms 2 into 10 power 16. So what remains here? Here, if you combine this one, it remains a silicon atom with 10 power 16 boron atoms. Borons means what? It's a p-type semiconductor. P-type means majority charge carriers are holes. So therefore, here silicon plus 10 power 16 holes will be there. So finally, silicon plus 10 power 16 holes means is what type of semiconductor it is? It is a p-type semiconductor. It is a p-type semiconductor. And in that p-type semiconductor, what are majority charge carriers? Holes. And what is that hole concentration means? 10 power 16 hole concentration will be there. So if all the dopants are fully ionized, the material is a p-type semiconductor with 10 power 16 boron atoms per centimeter cube, or 10 power 16 holes. P-type semiconductor with 10 power 16 holes. So this is the problem which has been asked in previous GATE examinations. So please consider this one, and we'll go with the next topic, which is called mass action law. Mass action law. This is as you know that at a constant temperature, the concentration of holes and concentration of electrons, its product is nothing but a constant. That is called as a mass action law. That means product of electrons and product of holes is nothing but a constant. So what is that constant here? As you see here, we know that in intrinsic concentration N is equal to P is equal to Ni for intrinsic semiconductor. In intrinsic semiconductor. Now if you apply for N into P, then it's nothing but Ni into Ni. So therefore you get N into P is equal to Ni square. So where concentration of electrons into concentration of holes, product is nothing but a constant which is called intrinsic concentration Ni square, where Ni square already you know that Ni square is equal to A naught T cube e power minus Eg naught by kT, where it is directly depends on temperature T. Now using this mass action law, we can able to find the majority charge carriers and minority charge carriers present in p-type semiconductors and also n-type semiconductors. So here, for example, if it is a p-type semiconductor, let us see, if it is a p-type semiconductor, then we have here Np into Pp is equal to Ni square. Np into Pp is equal to Ni square. Np, which is in p-type concentration of electrons, and this is Pp. Pp can be written as acceptor concentration because it's a majority charge carriers, holes majority charge carriers. These majority charge carriers are called acceptors. So therefore I can write this one as Na, since Pp is a majority charge carrier which is called acceptor concentration Na. So therefore Np is written as Ni square divided by Na. Ni square divided by Na. So that means we can able to calculate a minority charge concentration in p-type, because electrons, N is nothing but electrons is minority concentration. So minority concentration in p-type, can be calculated by using this formula which is called Np, that is equal to Ni square by Na. Similarly, we can calculate for n-type semiconductor also. For example, in n-type semiconductor, concentration of electrons into concentration of holes is equal to Ni square. So I can write this one as Nn into Pn is equal to Ni square. And in n-type semiconductor, majority charge carriers are electrons, and electrons are called as donors. So therefore I can write Nn as Nd, donor concentration, Pn to Ni square. So I can write this one as Pn is equal to Ni square divided by donor concentration Nd. So that means here it's nothing but called as minority charge carrier concentration holes, minority which are nothing but holes in n-type semiconductor. So if I know donor concentration, I can able to calculate minority charge carrier concentration in n-type semiconductor. Whereas here, if I know acceptor concentration, majority, I can able to calculate minority concentration of electrons in p-type semiconductor by using this mass action law, which is Np is equal to Ni square by Na. Here Pn is equal to Ni square by Nd. So this is what called as mass action law. Thank you so much. Thank you.